Hello everyone and welcome back. My name is Mr. Covalt, and in this video we're going to be going over dynamic equilibrium between liquid and vapor. So let's get into this. So in my previous video we talked about vaporization or evaporation and condensation. So now we're going to kind of talk about it together. So let's go back to our Erlenmeyer flask. We got a flask and we're going to close it up, and we got some water in there, right? So we got to close up with the stopper, close up the Erlenmeyer flask with the stopper, so that way we have a closed system, because that's going to be important for reaching dynamic equilibrium. Okay, so we've got this closed system. So here I have a picture of the water molecule. So every circle, every particle here is a water molecule, and so this is liquid, so it's liquid is on the bottom, and it's a closed system, as I said. And so they're moving around. The particles are moving around here, and we don't have any particles in the vapor phase right now. So this is like right when you poured into the Erlenmeyer flask and you stoppered it up. So this is before any sort of evaporation occurs. So everything is at the liquid stage. It's in the liquid phase here. And so they're moving around. And as we said, at the surface, if you have enough momentum, if you have enough kinetic energy, then you can break free of the attractive forces at the surface. And then you will become vapor. So you become part of the vapor phase. So in the beginning, the rate of evaporation is going to be all that we're concerned about, because we don't have any vapor up front. So we can't talk about condensation. We can't talk about the opposite reaction or the opposite process. So at the very beginning, all you have is liquid. You have no vapor, and so you have just evaporation occurring. So at the very beginning, as soon as you get one particle or one water molecule to break free, now you have a vapor phase. So let's draw that in. So let's say one of these breaks free, and then you've got your vapor particle. So here, let me draw that differently. Where's my eraser? Right, so here's my particle that's in the vapor phase. I'm going to put, there we go. Okay, so now I have a particle that's broken free in the vapor phase, and that's going to occur more and more. So the rate of evaporation is going to be larger than the rate of condensation in the beginning. Right? So in the very beginning, because we don't have any vapor particles, right? So this one's not there. So without the vapor particles, you don't have condensation. So the rate of condensation is 0, right? But then the rate of evaporation is some amount, right? Some number of particles per second, right? But as soon as you get water molecules breaking free of the surface and joining the vapor phase, now you're going to start to see the opposite process, which is condensation. So let me draw another particle. So condensation will occur when you have a particle in the vapor phase, a water molecule in this example. So this water molecule, if it hits the surface again, it could be sucked back into the liquid phase if the attractions are strong enough and if the kinetic energy of the molecule here is low enough, right? So this particle, when it hits the surface, could be absorbed back into the liquid phase. Other particles at the surface, if they have enough energy, can be released and break free from the attractive forces at the surface of the liquid, right? Just like that particle there. So as the process of your evaporation occurs, more and more particles are going to join the vapor phase. The more particles that join the vapor phase, the more likelihood that you're going to get more particles striking the surface, right? They're going to combine, they're going to come back and hit the surface, and then they're going to be reabsorbed into the liquid phase, right? So as time goes on, as more is evaporated, more particles are going to join the vapor phase. Now remember, this is a closed system. It's a closed Erlenmeyer flask. I have a stopper on the flask. So no particles are going to be released. So as more of the liquid evaporates, more particles are going to join the vapor phase. The more particles that are in the vapor phase, the more collisions you're going to have back with the surface, and therefore it could be reabsorbed, and you have the condensation process occurring more quickly. So as the particles grow, as more and more particles join the vapor phase, you're going to get more collisions with the surface, and then you're going to get more condensation. So the rate of condensation is going to go up, right, during that time. Now, what about the rate of evaporation? The rate of evaporation is not going to change at all, right? Assuming a few things, right? So we've got this container, right? We've got a liquid. So we're assuming that we're going to have enough liquid in here to reach what is known as equilibrium. Now, let me talk a little bit about that. So there's going to reach a point where the number of particles you have in the vapor phase is going to be enough such that the number of particles that are hitting and being reabsorbed into the liquid is going to be equal to the number of particles that are breaking free from the liquid. So as a particle gets absorbed into the liquid, a particle is going to be released. And so you get a rate of condensation where the particles are being absorbed equal to the rate of the evaporation where the particles are being released, and that is known as dynamic equilibrium. Dynamic because you have a constant change going on. There is still change going on. It's still dynamic in the sense that you still have particles being evaporated, breaking free from the liquid, and you still have particles being absorbed. So, but they're just different particles. What's equal, where the equilibrium comes in, is the rate of each of the processes. The rates are the same. So the rate at which the particles get absorbed and which is the condensation process, the rate of the condensation process is going to be equal to the rate of the evaporation process where the particles are being released. So the number of particles being released from the liquid phase into the vapor phase will be equal to the number of particles being being absorbed into the liquid phase from the vapor phase. And so we call that point at which the rates are equal is called the dynamic equilibrium. Okay, so now let's go back to the rate of evaporation. The rate of evaporation during this whole time stays the same. Why? The reason is because, well, one, we're not changing the surface area. Remember, this is a closed system. It's an Erlenmeyer flask or some sort of flask. You're not changing the flask. So the surface area is not going to change, right? So the surface area stays the same. We're not changing the temperature, right? So the average kinetic energy of the particles stays the same, right? So, and we're not changing the attractive forces between the particles. We're assuming this is water. Water has hydrogen bonding. That's not going to change, right? It's still hydrogen bonding. So throughout this whole time, the rate of evaporation should be constant. What's going to change over time is the rate of condensation, because when we start from the very beginning, we have 0 particles in the vapor phase, so zero rate of condensation, because there's no particles to go back into the liquid phase. But as soon as you get some particles evaporate into the vapor phase, now you start to have condensation, because now those particles can hit the surface and be reabsorbed, which is the condensation process. So in the beginning, you have 0 condensation, the rate is 0, but as soon as you start getting particles, the rate goes up, and you'll get more and more particles, because the rate of evaporation is going to be higher than the rate of condensation, because you have more particles here at the surface than you do up in the vapor phase. But as time goes on, more and more particles will be in the vapor phase, therefore increasing the collisions with the surface, increasing the number of particles that is going to be absorbed back into the liquid, and therefore increasing the rate of condensation. So here you can see over here a graph of what it looks like. So at the very beginning, you have the rate of evaporation being at here, and that's the same from the very beginning. So as soon as you put your water into the flask and set it there, the rate of evaporation is going to be a certain amount. And again, this is a closed system. So here, we start at 0 because we don't have any particles in the vapor phase, but as soon as you start evaporating some of those particles, now the rate of condensation starts to go up. And it's going to go up and up and up, because remember, the particles are increasing in the vapor phase. The more particles you have, the higher the rate of condensation. And then it gets to a point where the rate of condensation and the rate of evaporation are the same, and that's when you reach a dynamic equilibrium. Okay, so that's the explanation of the dynamic equilibrium between liquid and vapor. Now you can disrupt the equilibrium, right? There's a couple ways you can do that. But one way I could do that is by taking the stopper off of the Erlenmeyer flask, right? If I take the stopper off the flask, I've now released the particles that were in the vapor phase. Now they can go out of the flask, and now the concentration of the particles decreases. So now the rate of condensation will not be the same as the rate of evaporation. And so we've disrupted the equilibrium. If I put the stopper back on the bottle or on the Erlenmeyer flask, I can now build up those particles again until I reach equilibrium once again. So you can disrupt equilibrium by taking the stopper off. You could also, if you change the volume, that would disrupt the equilibrium as well, but we won't get into that in this video. Okay, so now that we've talked about dynamic equilibrium, let's talk about the vapor pressure at dynamic equilibrium. Okay, welcome back. Now let's talk about equilibrium vapor pressure. So again, we have our closed Erlenmeyer flask. It's got the stopper on it. We've reached equilibrium. We've got a certain number of particles in the vapor phase. And so the rate of condensation is equal to the rate of evaporation. So we've reached this dynamic equilibrium. So now that we have that vapor, we could talk about the pressure of that vapor. So let's go back to the ideal gas law equation. So we have PV equals nRT, where P is for pressure, V is for volume, and the little n is for the number of moles of your gas. R is the ideal gas law constant, and T is for temperature in Kelvin. So we can manipulate this equation by dividing both sides by volume, and we get P for pressure. Pressure is equal to the number of moles over the volume multiplied by RT. Now, you might recognize this right away as the number of moles over volume. Well, that's the same as concentration. That's how we measure concentration, number of moles or a given amount of substance in a given volume. So we have, that's what we mean by concentration. So we can replace this N over V with concentration. So remember, anytime you have square brackets around something, that means concentration of. So we have the concentration of a gas multiplied by RT. So there's a few things we can get from this. One, if the concentration, remember square brackets means concentration, if the concentration and the temperature are constant, then that means the pressure of the vapor stays constant. So the vapor pressure, what do I mean by vapor pressure? What I mean by vapor pressure is the pressure due to the vapor that is above the liquid in a closed system, in a closed container, right? So at some point, you're going to reach equilibrium, that dynamic equilibrium we just talked about. At that point, you have a pressure due to the vapor that's above the liquid in the container. So as long as you keep the concentration and the temperature constant, then that pressure will also be constant. Vapor pressure, that's part of a mixture of gases, right? So it's not just the water vapor, assuming that we're dealing with water. In my example, it's water. It could be acetone, it could be something else. But whatever that vapor is, it's not by itself, right? Because before it started to evaporate, you had air in there, right? So when you put the water in the container and you closed it, you had air above the surface of the water. So you've got air in there, you've got oxygen, you've got nitrogen, you've got carbon dioxide, you got other things, right? So that means that the vapor pressure due to the vapor is only a partial pressure. It's not the total pressure in the flask, okay? Now, the partial pressure of the vapor at dynamic equilibrium is called the equilibrium vapor pressure, or PVAP, right? So when we reach the equilibrium, the pressure due to the particles in the vapor phase above the liquid is going to be referred to as the equilibrium vapor pressure. Now, there's a couple of things that will affect the vapor pressure of a substance. Different substances are going to have different vapor pressures, as we talked about before, right? When we talked about acetone versus water, acetone has weaker attractive forces, so therefore you would expect the evaporation to occur more quickly and more readily compared to water, right? So the rate of evaporation for acetone is higher than the rate due to water, so that will affect what the vapor pressure is going to be when you reach equilibrium, right? So here's a couple of flow charts I've got on the board, right? So let's talk about weaker attractions, right? So if we're comparing acetone or nail polish remover with water, the nail polish remover has weaker attractive forces. So the weaker attractions between particles in a liquid, if you have weaker attractions, then that's going to lead to a higher rate of evaporation. The particles are going to go into the vapor phase more quickly and easily because they can escape the weaker forces at the surface of the liquid. Higher rate of evaporation means that you're going to need a higher rate of condensation for equilibrium, right? Remember, at dynamic equilibrium, the rate of condensation has to be equal to the rate of evaporation. If the rate of evaporation is higher, then your rate of condensation also has to be higher to be equal, right? So that makes sense. So higher rate of evaporation means higher rate of condensation needed for equilibrium. Which also is going to mean that you're going to need a higher concentration of the vapor particles. right? In order to increase the rate of condensation, you need more vapor particles in the vapor phase, right? In order to make the rate of condensation go up, right? So this is going to mean, so a higher rate of condensation means that you need a higher number of particles in the vapor phase, which means you need a higher concentration of vapor particles, which then leads to a higher equilibrium vapor pressure. More particles in the vapor phase means more vapor pressure. Why? Because remember, where does vapor pressure come from? Or where does the pressure of a gas come from? It comes from the collision of the particles with the side of the container. More particles means more collisions on the side of the container, which means more pressure. So if you need a higher concentration of vapor particles, meaning more particles in the vapor phase, that's going to lead to more collisions with the sides of the container, which means higher vapor pressure. Okay, I hope that makes sense. Okay, now what about temperature? Let's go over to temperature over here. So, temperature, we saw before, temperature can influence vapor rates or evaporation rates. So, how is that going to affect the vapor pressure at equilibrium? Well, if you increase the temperature, remember, temperature is related to the average kinetic energy of the particles, how fast they're moving. So if you increase the temperature, you're increasing how fast they're moving and how much kinetic energy they have, and therefore the likelihood of them escaping into the vapor phase, right? They have more energy to break free from the attractive forces at the surface of your liquid, right? So higher increased temperature means that you're going to now have an increased rate of evaporation. So the rate of evaporation goes up because you have a greater percentage of your particles with enough energy to break free from those attractive forces at the surface. So therefore, you're going to need an increased rate of condensation in order to reach equilibrium. Just like I said before, increased rate of evaporation means that you now have to increase the rate of condensation to be equal, okay? Which means that now you're going to have to increase the concentration of vapor particles needed in the vapor phase to get that rate of condensation needed, which means that now you're going to have an increased equilibrium vapor pressure, because now that you reached equilibrium, right, you had to go higher, right, to reach equilibrium. So you had to have more particles in the vapor phase, which means more vapor pressure, right? So both increased temperature is going to increase the vapor pressure. Weaker attractive forces is going to increase the vapor pressure in your container. Okay, so I hope that was helpful. If you like this video, then please hit the like button down here somewhere. Also, subscribe to my channel. Put a comment down below. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.